Välkomna till Livbojen, din fotboja i kulturhavet, tror jag att den heter. Och idag är det jag som heter Roger och det här är min kollega Ryan från Kalifornien.
Here's our latest FONTÄN Hughes magazine, and if you look, there is a article written by
Roger Klangs.
Basic Trajectories, Conjecture Set. Okay, let's get into this. My first question is, what is a Oumuamua? Oumuamua.
Oumuamua is an interstellar object.
It's an object.
It's an object.
What object? A comet, an asteroid?
It's an asteroid, you can say.
Okay. So, and they've named it.
Yes, because it's not very often that it comes objects from another solar system into our solar system. It's very rare. It doesn't come into the Earth's atmosphere. It's in space, inside the sun's gravitational field.
Okay.
But how far out from Earth or from the sun it is, I'm not sure about that.
Okay.
But it's quite a bit, and it's.
Does it go into our galaxy?
It's in our galaxy, but it's probably always been inside our galaxy.
The Oumuamua.
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 Is that a Hawaiian?
Yes.
It is.
Yes.
I guessed it.
Yes, but I'm not sure where the name comes from, what it means.
But it is Hawaiian language.
Yes, it's got a meaning.
Etymology or whatever.
Oumuamua has got a meaning, the word.
Okay. All right. So that's your abstract, is to go with that. And then you go on with the article about how energy and the gravitational pull, somehow something steals. Can you explain that?
Well,
you know what I mean?
Like it's just a name for something. It's a word that I use, but steal is just.
Yeah, you have it in quotations.
Yes.
So it is a word you're using because lack of a better word or something.
Exactly.
Does it borrow the energy?
Only if it's in orbital trajectory. It's only if it's in an orbital trajectory. But
orbital trajectory, does that mean it's just going around in a circle?
Around an object in a circle. Yes.
An object in a circle.
It's not a circle, but it's
an
oval,
ellipse, elliptical,
elliptical or something.
And it stays in the same pattern, the same form or whatever.
Yeah, if it's stable, it does, and it should. Like planets, they're in a stable orbit.
Yeah, planet Mother Nature. She's just going. Just around and around and around.
Exactly.
Yeah. What is Roger? Did you draw these graphs?
Yeah, I did it with a tool from Texas Instruments.
TI?
Yeah.
Those guys are great.
Yeah.
They know how to make calculators.
They do.
Expensive, but I mean, they get the job done.
You can see the image. It's got an object moving around a star, the round little circle, and at the outskirts of it there's a smaller body or a body that travels within the gravitational field of the small object.
Are you hypothesizing, or is this a
no,
fact?
No. It's just like when
it's a fact.
Yes, it's a fact. When you use planets like Jupiter, for accelerating satellites or like the Voyager 1 and Voyager 2.
Okay.
You use planets to increase the velocity of the satellite.
Yeah, the speed.
The speed of the satellite, because it's moving so close onto the planet that it accelerates and get a bigger velocity, a higher velocity.
Is it like a swing?
Yes, you can say that.
I was going to say slingshot, but slingshot is pulling back.
Well,
but a swing is like, you know how when you're a kid you start out here and you go a little bit, and then a little bit more, and a little
sometimes
bit more, and a little bit more, and a little bit more, and then
sometimes you shouldn't use what's it called?
Earth science?
No. Yeah, well, we can say that.
I believe that there's science that can be done on the Earth, but not in space, and vice versa.
Yeah, I guess so, but
like if you shine a flashlight on a ball, it will be different than if you shine a flashlight on a ball in outer space.
In what way?
I don't know. I want to get back to your orbit, your image 22 here. So the star has a gravitational pull. And the Umomo is going around B, and then it pulls into A. It changes its orbital trajectory. It gets smaller because the gravity's pulling it in, yes? Is that what's...
Let's say that is Umomo.
Yeah.
But it's not.
Going around in a circle.
It wasn't so close to Earth. If Earth is a small round circle,
yeah,
it wasn't so close to Earth that it got affected by Earth's gravitational field.
Right, but it does get a new orbital trajectory because
of the sun, yes.
The sun,
but
or
we're
whatever,
talking
yeah.
about a system like with the star in the middle and an object like a planet circling around it, and a body like this.
Yeah, like the sun is a star
going around.
And we're going around according to heliocentric. Are we going around, or is the sun going around us?
Let's say that this body circulates or circumcises or goes around the Earth here.
Not circumcises, circumvents.
Circumvent, sorry. Yeah, I know, I'm not English speaking.
Hey, you're doing great. You're doing great.
Yeah, okay. But anyway, the Earth is going to be drawn a little bit towards the body.
Okay.
So that it gets a new orbit like this one.
That was my question. So it's going around one, and then something happens, and it moves in.
It will get a new orbit.
Is it possible that it's going around and gets pushed out? Are there
pushed
orbits?
out?
Yeah, the opposite.
No.
The opposite is not possible.
No, it's not. Since it's going around the sun, it's in a stable orbit. But if another body sort of intervenes with the orbit for the object, then it's going to get a bigger radius from the sun, and it's going to move slower. Look, if you have a track, a sprinter track, you know.
Yeah.
And you have different courses around the track.
You mean like the EDROT, the athlete?
Yeah.
Goes, shoots the gun. Usain Bolt runs around.
Yeah.
Yeah.
And if you start from the same point on that track, from the very same starting point, but they don't. But if you did,
yeah.
Then if you are in the outer track, you would reach the goal later than if you're in the inner track.
Yes.
So but that's why they differ the starting point, so that when you are on outer tracks you get a shorter distance, they are further ahead.
Yeah, when it's the Olympics, they stagger them.
Yeah,
because of the distance.
Exactly. But that's not the case here, because even though it's not an immediate transfer of position for the object, the small object, or
that's another question. How long does it take for this to happen? Do you know? Do you?
That happens.
Light years?
No,
hundreds of years?
No. That happens immediately.
Immediately.
As soon as the smaller body gets into the gravitational field of the larger object, like the Earth or something. But
how come it doesn't keep going into the star? If it's in the gravity at B and it gets sucked into A, why doesn't it get all the way sucked into the star? You know,
we were looking at this one.
Yeah.
But if we're talking about this one, like this.
Well, yeah. Yeah, you got like 2 or 3 graphs on there.
If the body, the small body, circumvents the larger object on the inside of the larger object, then the larger object, of course, gets closer to the sun.
It will keep going and going and going.
What?
It will keep going to the big gravitational.
No. The larger object will just decrease its radius so that it gets a faster velocity around the star.
That's what this article's about.
Yeah.
Got it.
Okay.
Got it. Okay, so you're talking about the speed at B, and then it goes to A because it got close to the star, the body, and then it goes smaller into A, but stays. So does it get faster the smaller it goes? Just like the people running on a racetrack.
What the smaller it goes? What do
So
you mean?
so if I'm
smaller radius.
Yeah, as it gets smaller and smaller,
would
I get faster and faster?
Yeah.
Because I'm going 2 billion light years, let's say.
In the orbital plane, it gets faster.
And then I get sucked into A, and now it's less distance to travel, so it would be faster,
yes,
right?
in the orbital plane, it is faster. So
I think you should, no offense,
yeah.
I don't think the article should be titled Basic Trajectories Conjecture Set. I think it should be titled Advanced Trajectories Conjecture Set.
Advanced.
Advanced. I mean, I had to read it twice and now talk to you. No offense, Roger. It's a cool article.
Yeah.
I mean, I had to go to Google and look up some stuff. I didn't know the moon was moving away from the Earth 3.8 centimeters a year or something.
Like.
Because that's interesting. I'd like to know, how does that...
3.8 centimeters per year. It's moving away from Earth.
Yeah, moving away. How does that affect the tides and the gravitational pull that the moon is?
In the long run,
you know,
for billions of years.
I read your calculation. It's good.
Yeah.
It makes sense. I punched it in. Mm-hmm. It's, you know, I'm pretty sure you probably did like 10 revisions or something like that, and you check the math 100 times. You know, you got to be really precise when you're writing stuff about
it wasn't that difficult.
Space, life in general. I mean, you can't troll people.
Not this calculation wasn't so difficult.
Well, you're a smart man, so
I'm not. I'm not smarter than you are.
I think with this space stuff you are. I don't read too much about the space. You know, it's interesting, but it's not.
But it's interesting that because
it's not as mainstream as it used to be. So, you know, plus playing the piano is so much funner, I guess, or fulfilling. I don't know. It's a good. I read the article. It's good. It's good. Folks, you got to read it. Now you know a little bit more about it. You'll know who Roger is.
Yeah.
The writer of. Are you going to write some more articles? Are you going to have a follow-up?
Yeah.
With the same... Not
the same exact topic, but...
space.
Adjacent topic.
In space.
In space.
Yeah. Is your favorite song Space Oddity by David Bowie?
No. Du är min bäste vän.
That's a good one. Yeah, this is a really cool article. I after talking to you now, I get that you're talking about more, velocities, and because like you said, the basic trajectories.
Conjecture Set.
Conjecture Set. Yeah. Thanks for watching.
Thank you.